Thank you, and I'm happy to be here today, this afternoon. So my name is Tamar Eilam. I'm an IBM fellow, and I work in the Watson Research Center in New York. And I am going to talk with you about the journey that led to Istio. Now, before we even start, a little bit of a show of hands. So raise your hand if you know what is Istio. Okay, quite a few people. Raise your hand if you already had a chance to download Istio and play with it. Okay, cool. All right. So I've been working in this area longer than I care to admit. And I'm lucky to be able to witness and also to contribute to the evolution of ideas in the space of cloud, DevOps, and microservices. So if you don't mind, I'll take you to a little bit of a short trip back in time. So who remembers 2004? Who is old enough to remember 2004? I know you are. So back in these days, software was developed in a quite different way. And we had developers and we had operators. And around 2004, people, including myself, started noticing the gap between developers and operators. And this gap was organizational, and this gap was also cultural. So operators were used to doing things quite differently, lots of manual processes. And this miscommunication between developers and operators led to a lot of inefficiencies and unpredictability and risk. So back in these days, I started working on technology that will alleviate this problem. And basically, I came up with this idea of a desired state-based management, where we had a language, and that language is something that both developers and operators define the desired state of the system. And then I worked on techniques to dynamically generate the automation to deploy an application based on that desired state model. And it was messy. It was very messy. And the reason why it was messy is because there are lots of interdependencies between different software components. And these interdependencies led to very fragile automation. The automation was fragile because we had lots of temporal dependencies between steps of the automation, and also because we needed to copy a lot of configuration data from one place to another, from one tool to another tool to different hosts and stuff like that. All right, so fast forward to 2009. 2009 is where the DevOps term was coined and the DevOps revolution started. And it was cultural because we brought together developers and operators to work together since the inception of a project. And it was also technological because it was about, rather than having manual processes, now automating everything, automating the configuration, automating the deployment of the application, and versioning control everything in a consistent, unified process, which is the continuous delivery process. So that was a big step forward. Nevertheless, and this, big step forward, repeatability, less fragile, less risk, reduced risk. So this was all good. Nevertheless, software was still very complicated. And it was still a monolith. And these nasty interdependencies between software components still existed. And one life cycle to something which is that big, it's very hard to modify it. And microservices. So around 2011, the conversation really expanded. So if we focused on deployment and configuration, now we start talking about development and management, and we start talking about how to develop your code in a way that it's going to be easier to manage in production as a continuously running service. What are the architectural patterns and what are the design patterns that are going to simplify the code so it's going to be easily managed? So the goal was agility, and the mean was loose coupling. And when I say loose coupling, I mean loose coupling which is obtained by using consistent, well-documented APIs. Loose coupling which is obtained by denormalizing the data. And loose coupling which is obtained by standardizing the way we're dealing with dynamic binding, the way microservices bind each other, the way with configuration. So in one word, loose coupling basically means that you have an entire team, a small team, that is taking a full responsibility for the microservice since the development to the time that it runs and managed in production. And that these separate teams, separate independent teams, can work on different microservices, and they don't need to coordinate. That means that they can make much faster progress, much quicker progress on developing these microservices and running them. It's also about resiliency, and part of the cloud native principles is how you deal with resiliency through patterns such as circuit breakers and bulkhead patterns. So obviously, now that you know a little bit about my background, you know why I was really excited about microservices when they came out. So before I continue, I wanted to point out another thing. So if we talked about DevOps, we talked about microservices as the two pillars for agility. Containers is obviously the third pillar for agility. And that's because containers are portable. That means that development and production environments are similar. There are no differences. So they're development friendly, they're lightweight, and they're very suitable for cloud native. All right, so I was very excited about microservices, and I'm working in IBM research, so I took a team and we started thinking together about what can we do in order to help our customers simplify the way they develop microservices, they deploy them, and they run them. Now you may think, okay, why would we simplify microservices? Because microservices are already simple. That's the main premise of microservices, they're simple. And it's true. So basically what's going on now is the complexity is shifting. It's very easy to develop a single microservice, and a small team can contain the work, and they don't depend on anyone. But you're going to end up in a situation where you have an application that is running on the cloud and is consisting of multiple interconnected microservices. In fact, it's a very dynamic environment. The whole idea is to get to agility. So that means that you're contributing new code, new versions. And at any point in time, you're going to have multiple interconnected microservices. And for each microservice, you may have multiple different versions running side by side with traffic splitted across them. So in that environment, how do you gain insight? How do you understand what's going on? Who communicates with who? How do you ensure security? And how do you troubleshoot? So that's the questions that we're trying to answer in IBM research. And we took a step back and we thought about, okay, we need a microservice mesh. We need a platform that is going to enable our customers, the enterprise customers, to go and develop microservices. What are the properties of this microservice mesh? And this is what we defined. So we wanted it to be a polyglot. We didn't want to constrain ourselves to just Java. That was one property. Second, we didn't want to require any changes in code. So you already have your application. You don't want to rebuild it. You don't want to restructure it in order to include some libraries, right? We don't want to necessitate that, okay? The third thing is we wanted to enable experimentations and insight. And that's really important because when we talk about agility, we don't just talk about the speed of delivering new code. It's not just about speed. It's really about insight. You gain insight, and the insight informs your next steps. Of course, we wanted to be resilient, and we wanted to be able to do resiliency testing. And we also wanted it to be simple. Okay, so this is our 5 goals. And based on these goals, we defined the following principles. Because we wanted it to be a polyglot, which means that you can run your microservices in any language, we externalized the logic of the routing, the load balancing, and the failure handling as a separate process, which is a router, which is running side by side with the application. So it's a separate process. In the container world, it's going to be a different container. In Kubernetes, it's going to run in the same pod. Okay, and by doing that, we also achieved the first of all, we achieved the property of polyglot because you don't have to rebuild your applications with libraries because the logic is externalized. So you have 2 different independent life cycles, and the sidecar is part of the platform, but the application is something that you control. We also achieved the second property because now we don't require any changes to the code. Okay? In order to enable experimentations, we thought we need smart routing. So smart routing based on the content of the request in layer 7 means that you can split the traffic based on all sorts of criteria. So it could be based on the percentage based, which is useful. It could be based on the content of the request, such as the geographical location or user identity. That allows you to do A/B testing, to run 2 different versions and do A/B testing. So we needed that to be configurable, which means that our sidecar must be configurable with these routing rules that will allow splitting the traffic. The other thing is we wanted resilience, right? So for resiliency, we wanted to be able clearly to program the sidecar with failure handling parameters, timeouts, and retries. But we wanted more than that. So remember, each individual team is working on an individual microservice, and they don't coordinate, right? So every one of them comes with their own timeouts and retry parameters in that interconnected network. But we don't know what's going to be the interaction, the interplay between these parameters, because lots of very weird things can happen with this interaction. So what you really want to do is you want to test the resiliency of the entire service mesh. Okay? So how do you do that? So we came up with the idea of injecting delays and failures that are very localized with control in particular places in the network, so that you can simulate a failure and you can see the effect. You can see how the service mesh, how your application behaves as a whole. So that was something that we needed in that sidecar, the ability to do that. And last, we wanted to be easily used. So think about all of these sidecars controlling the traffic. We wanted a centralized control plane that allows us to define all of these rules and to push them into the sidecar from a centralized location. So this is our design goals, and we went and prototyped and implemented it, and that's what became the project Amalgamate, which we open sourced in May 2016. So as you can see, we have a control plane, and we have these sidecars, and we have multiple versions running side by side, and you can configure the routing rules between them, and you can inject failures. So 2016 was a very interesting year because based on Amalgamate, we started a conversation with Google. And I think it was very obvious that the concepts are valuable and that they go beyond the value that Kubernetes already provides. And we all love Kubernetes, but that went to the next layer. We also, another thing that happened is that the company Lyft open sourced Envoy around August 2016. And Envoy is, if you don't know, it's a C++ programmable router that is very highly performant and is battle tested in production. And it's programmable, so we really liked it. And we thought that's going to be a good implementation of our sidecar concept. So it was a very natural decision for IBM, Lyft, and Google to come together and to decide, hey, let's work together. Let's take the Amalgamate concept, let's take Lyft, and let's work on something together that is going to be this and much more. So around August 2016, we started working together. And in around May or June 2017, we announced Istio. And during that period of time, we were busy creating Istio. So you see, this is the architecture of Istio. And you see the control plane, which includes Pilot. Pilot basically includes all of the concepts that we put in Amalgamate. So we just delivered the code as this Pilot component, which really configures the routing rules in all of the sidecars. We also worked with the Envoy community in order to put in Envoy the ability to inject delays and failures, because that was something that was missing, and it was important to us. And we also worked with Google in order to expand the capabilities of Istio. So now we have 2 different new components. We have Mixer, and Mixer is a central point that you can collect telemetric data, but it's also a place where you can define policy that governs each one of the communication between the microservices through role-based access control. And we have a new component which is called Citadel, and it was previously known as Istio Auth, that is responsible for the authentication. So this is a really nice example of sort of the community coming together in order to solve an industry issue, and it's also a lot of fun to sort of work together. So in the time left, let me just go quickly through the capabilities of Istio. So as I mentioned, we have intelligent routing, and intelligent routing allows A/B testing and canary releases. This is two different patterns of intelligent routing that you see here. Traffic steering, which is basically, okay, I'm gradually moving the traffic to the new version to service B prime, and that allows me to do some canary testing to see that everything is good. And then the second one is a little bit more complicated, where I'm looking at the content of the request. So I route all of the iPhone users to the service B, and all of the, to the service B prime, and all of the Android users to service B. And then you have here an example of a rule which is even more finer grained, and it basically defines that only user JSON can see version number 2. And that is obviously useful if you want only the testing team to see particular version so that you can test it before you're making it public. Okay, so we have resiliency, and resiliency is achieved through timeout and retries parameters that are configured in all of the sidecars. So you can easily configure this, and the first example that you see we're basically putting a timeout of 10 seconds. And in the second example, we're also limiting the number of attempts to 3. So this can easily be done through these types of rules. More than that, we are able to inject delays and failures to test the resiliency. And here you see an example where we're introducing a fixed delay of 2 seconds in a particular place in the network. So this is a proof of concept that we worked in IBM research in my team. And what it's doing is basically it's providing a simple dashboard that allows you to easily control these configuration parameters and inject delays wherever you want to inject them. But then you can visualize the effect in the network. So what you're seeing in that picture is every bar, every call for bar is a microservice. Then the gray area is the communication between these microservices. And the pink area is the ratio of these requests that are coming back with error codes. When you look at this, when you inject a failure, if you have a problem, you're going to see the effect visually very, very clearly. And what you're going to see is the area that is pink starting to expand. And then it's starting to expand to other areas of your mesh. So obviously, you don't have resiliency because you have the cascading failures. OK? So we have the policy, and I mentioned this. So through Mixer, you can now define role-based access control. There is a way to very flexibly define role and role binding. And Mixer is also extensible. So you can extend it, and you can integrate it with your own favorite product, organizational product, to enforce whatever rules you have. And we also have telemetry collection. And this is something that customers want to use first because it's easy. It's out of the box. And it gives you a lot of valuable data, just like out of the box. And so just by the fact that we're running all of the traffic through Envoy, and Envoy is a router at layer 7, that means you have a lot of available data. So that means you're getting the bandwidth, the latency, the protocols, the error, the return codes, all of that, the latency. Yes, I did say latency. All of this, the logs, and all of this is available to you, OK? Now, we are also integrating with other open source projects in order to do the rich data collection. So we're using Prometheus for metric, and Fluentd for logs, and Jaeger for tracing. And data visualization can be obtained through Grafana. And again, since Mixer is extensible, you can add your own favorite tool to process the data and to do the visualization of the data. So you're gaining insight. And this is the first thing that the people want to do. They want to gain insight. So this is just like showing you some of the visualizations that are obtained through different open source projects. Okay, let me talk a little bit about the status. So we just released 0.8, and there are lots of new capabilities. It was a major release leading to 1.0. And what we did is we revamped the traffic management model. So we reorganized the way rules are defined, and now it's more like host-centric. We also addressed the communication between Pilot and Envoy. So now it's streaming-based, which means that it's more performant and it's less error-prone. We changed the way we're dealing with gateways. And we also have a feature which is called Istio a la carte, which allows you to just deploy some portions of Istio. For example, you can only, because it's all loosely coupled, right? So you can only pilot plus Envoy and gain this smart routing if that's what you're interested in, for example. This is not in the list, but we also started implementing something which we call Istio multi-cluster, which is obviously very valuable for in the hybrid cloud space. And we have a vibrant community, which is really nice to see that there are lots of startup companies that joined right from the beginning and are contributing. So it's really very nice to see all of the work that is going into this project. So I started my presentation talking about the past, and I want to finish by looking at the future. So Istio And Beyond. I just like to mention two different experiments that we're doing in IBM research, which leverage the Istio capabilities, but is going much further with them. So one of them is something that we call Istio Analytics. And Istio Analytics, so as I said, we already have an integration with Open Tracing and with Jaeger to do to understand them, to trace requests through the chain of microservices. Here we're taking it a little bit a step further, and what you're seeing here is that we're doing some statistical analysis of the average and averaging, and we're able to break a request in order to understand what is the exact latency of the communication, the average latency of the communication, but also what is the compute time, which is the yellow bars there. This is the compute time, how long does it take to compute before it can go to the next microservice. Further, what you're seeing is some green needles over there. And these green needles is basically, we're comparing two different versions. So we're comparing these two versions, and if they're quite similar in the compute time or the latency, then you're gonna get a green needle. But you have one case here, if you see here in the bottom, where you get a red needle. And red needle means that the new version is much slower than the old version, which may indicate that you have a defect, and you may want to take a look about what's going on there. So this is all going into A/B testing, and when we started this, we started A/B testing with a single microservice. So we looked at a single microservice and we compared it with the older version. But here we're looking at the entire network, because if you change one, there could be some effect on other places in the network. So that's what we're doing here. And then the last experiment that I want to mention is we're playing with AI techniques in order to automatically auto-tune the failure handling parameters. Because one thing that we heard from our customers is that they actually have no idea what to put. They don't know what should be the timeout and what should be the retry. So we're sort of doing it for them, and we're continuously dynamically updating these parameters so that they're going to be optimal. So that's just like a look in the future. Into the future. And okay, so this is what I wanted to say today. And just as a summary, I'm very excited about this project. And this really help enterprises to deliver innovation, not just, but also with security and with control and with insight. Okay, thank you.
So I'm actually going to ask the first question.
Yeah.
In your vibrant community, I'm going to ask you to add F5 to that list.
Oh, yeah.
Because we have an F5 incubator called Aspen Mesh that are developing enterprise services on top of Istio. So that surprises a lot of people. They're probably like, why is that F5 guy emceeing that talk? We're actually part of that community as well, because we know there are many different platforms. There are still many different apps that are like legacy kind of architectures, but there's a lot of the new stuff as well. So we're kind of evolving with that, and we're really excited to be working with Istio and contributing back as well. We've got a team of people out in Colorado. So so my one ask is that we get thrown up there as well.
Yeah, very, yeah.
And I very cheekily did that in front of an audience of witnesses.
But I will add F5.
So any questions from the audience for Tamar? That means you did such a good job that there was nothing left to ask. That's the only thing that could mean, I think.
Oh, here, there is a question over there.
Yes.
So when you've got these two proxies going out there, it's a layer 7 proxy?
Yeah, Envoy is layer 7.
I see. So is there any encryption that the proxy automatically adds, so you wouldn't have to make that?
That's exactly what's going on with the mutual TLS authentication, which is given by Citadel, and that's one of the things that, we're giving you security out of the box.
And the certs are all managed by the...
Yes, the CA. Yeah, Central Authority Management, yeah. Okay, thank you.